Right, so we have, if you have non-polar molecules, the forces will be London forces. Okay? Now, next one, we're going to work with polar molecules. Now, polar molecules are usually dipoles. Okay? Meaning that they've got a positive and a negative part to the molecule. Let's look at our first one, the one you find in your stomach, hydrogen chloride. Okay, what is the nature of the bond when you have hydrogen chloride? What is the nature of this covalent bond? Is it pure covalent, polar covalent?
Polar.
Why? How do you know it's polar covalent? 3 minus 2,1 makes 0,9. So it's a polar covalent bond. And the charge, the electrons are not shared equally between the atoms. So the electrons will spend more time with the chlorine than what they spend with the hydrogen. So this molecule as a whole is a polar molecule. You see, there is a difference between a polar covalent bond, where the electrons are not shared equally between the atoms, and a polar molecule, where the molecule is a dipole. It's got a positive side and a negative side. So what do you think would we call the intermolecular forces if we have hydrogen chloride molecules close together? Dipole forces. The hydrogen is polarized positively, chlorine is polarized negatively. So between the positively polarized hydrogen of one molecule and the negatively polarized chlorine of another molecule, you have dipole forces. That's your intermolecular force.
So in other words, the intermolecular force is dipole.
Yes.
One budget question.
Your intermolecular forces, when you have dipole polar molecules, will be dipole forces.
How can you have attraction with one force? Right? And which is asking why there's two hydrogen.
You have two molecules, so there must be a force of attraction between the two molecules. You can't have an intermolecular force between if you have only one molecule. Can't have intermolecular forces with only one molecule. So you need two molecules to have intermolecular forces. Forces between two molecules. So if that is one hydrogen chloride molecule, you need another hydrogen chloride molecule to have intermolecular forces. So the hydrogen and hydrogen won't attract, they will repel. But if they come close to each other and the chlorine of one molecule is close to the hydrogen of another molecule, there will be attraction. And it's called dipole-dipole attraction because this molecule is a dipole, that molecule is a dipole. They can also attract like this. But the problem like that is, no, I don't think it's a problem. They think that the bonding electrons could be repelling them. They won't be attracted by such a strong force that they stick together at room temperature. But there will be attraction. Hydrogen chloride is a gas at room temperature. What you know as stomach acid is a solution of the hydrogen chloride. Okay? So your forces of attraction, intermolecular forces of attraction would be dipole-dipole. Okay. Another one. Let's look at that sulfur dioxide that he discussed and that you did in 2.6. Can I go to the next slide? So sulfur dioxide. Yes. You want me to figure out the double bond story for you, or are you okay with that? Sorry? Please figure it out. So sulfur has how many valence electrons?
It has 6.
6. Okay. Oxygen has how many? 6. Okay. And there is a second oxygen that's got 6 valence electrons. So we all together we have 18 valence electrons that we need to arrange. Now we know that there will be molecules that will not follow the octet rule with all the atoms, but we must still try to follow the octet rule, and we must keep in our mind how many bonds an atom can form and try and follow that. The more you practice, the better you'll get. So sulfur is our central atom. And somewhere in your textbook, they've got the rules to follow the octet rule. Let's go and look for it. I think it's page 19 somewhere. Look on page 19. No, not page 19. Page 17. 17. Choose a central atom, almost always the atom with the lowest electronegativity. Page 17, just below steps.
17.
More, it says, like just above the middle of the page. Stop talking now. More complex molecules can be illustrated using Lewis notation. The octet rule is important for complex molecules. The elements of period 2 are especially true to the octet rule. So this book gives you some very useful hints that if you bother to go through them, you'll be wiser. It says choose a central atom, usually the one with the lowest electronegativity, so sulfur is our central atom here. Determine the total number of valence electrons in the molecule or the ion. Note the charge on the ion. The negative ion will have one more electron in total, and a positive ion will have one less. Always place one pair of electrons between each of the bonded atoms to form a single bond. So I'm just going to follow what they are saying. I already know that there are 18 electrons, and here they say I must place one pair of electrons between the atoms that are forming the bonds. Place the remaining electrons as lone pairs around the terminal atoms but not if the terminal atom is hydrogen. Start with the most electronegative atom. So how many more electrons do I have to...
Oh, you have
How many more
14.
electrons do I have? 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. Now there's nonsense. Wait, I'm just trying to teach you a skill. When the terminal atoms each have 4 times 2 pairs and there are still unplaced electrons, the remaining electrons are placed around the central atom. So that's what I've done. If the central atom has less than 8 electrons around it, move some of the lone pairs to a position between the central and the terminal atoms. So I think I'm going to move this lone pair of electrons there. Then the central atom has 8. The terminal atoms, each one has 8.
So, ma'am, why did the textbook draw the sulfur dioxide the way it is?
Yeah.
How do you mean?
It's on page, where is it now? It's on, not sure what page it's on.
There on page 23.
No,
Yes.
Yes.
really?
Yes.
Oh, yeah, there. Why is it like that?
It's the same thing.
The only thing is they didn't follow the Vesper theory, but now that Tyler has explained it to you, you can know. I don't like using the Lewis structure like that.
Yeah, it looks
I prefer the Cooper structure. So the lone pair of electrons will have a force of repulsion on the bonding pair of electrons. Sorry?
Ma'am?
Yes, Sadie?
If you moved and made another double bond, would you get it wrong?
Okay. There is only one double bond, but this now I'm going to teach you the new thing, the next thing. Who says that the double bond is between those two atoms? Who says that the double bond isn't? I'm going to leave the Lewis, go away. Who says the double bond isn't there? Okay? So with a double bond there, does it change the molecule's properties? No. But it is between two different atoms. It's in a different place. These are called resonance structures.
Okay, but ma'am, before you go on, if you created double bonds between each oxygen, instead of having oxygen being surrounded, does it change the whole thing?
Okay, I want you, the double bond between both oxygens doesn't exist in this molecule. But let's look at sulfur trioxide.
Are you done with the sulfur dioxide?
No, I'm not done with it.
You finished with the sulfur dioxide. Yeah, actually, can you write it down?
If you put another double bond here, then the molecule should be linear. Or which pair of electrons did you put into the double bond?
You see on top of the oxygen?
This one.
Yes, so I put it there.
Then how many electrons do you have around the sulfur?
Too much.
10.
10.
No, okay, this is what I did. Wait, hold on, let me count my numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, okay, makes sense.
Okay, thank you.
Wait, then.
Resonance structures are they are molecules where the double bonds have jumped atoms. They both exist. And you won't be able to distinguish between the two molecules because they will have exactly the same properties. If you go and read in your textbook, well, then lose out. Page 18 and 19, they show you resonance structures. It's just the position of the double bonds jump from one set of atoms to another set of atoms.
But they can't both be double bonds at the same time.
No. Resonance is what enables you to listen or to hear.
Yeah, I remember.
I explained it to you in grade 10.
Yes.
Because your cochlear's hairs have different lengths. And I also did the pendulum experiment with parrot, where if you shorten the string, the frequency increases. So in your cochlea, you have nerve hairs, millions of them, but they have different lengths. So they have different natural frequencies of vibration. My low frequency of vibration cochlear hairs have been damaged. So I battle to hear. Some people's high frequency cochlear hair gets damaged, so they won't hear the high pitched sounds clearly. Okay? So the way you are busy hearing things is because of resonance. The frequency of the waves that hits your eardrum causes the vibration and those little bones in your inner ear to hit and amplify the sound, and then the signals got a specific range of frequencies, and each frequency that is married to, that is the same as the resonance frequency of the cochlea, will make that thing vibrate. If you have seen a person singing, breaking a glass, if you've seen a video or things that, it's because of resonance. You can create a sound that has the same frequency as the natural frequency of another object, and that sound will make that object vibrate with an increasing amplitude. That is resonance. So here in chemistry, resonance means that the double bond could be there or here, but not both there and there in the same molecule. Okay. Page 18 and 19. Okay. I'm sorry, Uko, I can't spend more time on it. You need to go and read there on page 18 and 19 and maybe watch some YouTube videos. What? I'm not going anywhere. Mfihla Carlo, your talking is disturbing. Okay. I want to know what is the nature of the bond between sulfur and oxygen. What is the difference in electronegativity? It's 1, so 3.5 for oxygen minus 2,5. So the nature of the bond is polar covalent.
And it's a polar molecule.
Yes, because the electrons shared between the sulfur and the oxygen spends more time with the oxygen. The oxygen parts of the molecule is polarized negatively, and the sulfur would be polarized positively. And because of the shape of the molecule being bent, it's a polar molecule. So if you have millions of these sulfur dioxide molecules in a container, what will the intermolecular forces be? Dipole forces.
going to do stoichiometry again.
She said yes.
Of course we are.
That's the beautiful. Does it get harder or is it the same?
Stoichiometry, even if it gets harder, but it's better than other stuff in chemistry. Like, it's unbelievable.
Okay, you are going ahead to things that are not important at this moment. Good. I want to move on.
No.
Okay.
Wait.
So from the so the things that we need to know is what the nature of the bond is, we use electronegativities, and then the second thing that we need to know is the shape of the molecule. Some people say the geometry of the molecule, because the shape of the molecule will determine whether the molecule is polar or not. Okay? Like carbon dioxide.
That's linear.
Sulfur dioxide and carbon dioxide, it looks like it should be the same type of molecule. But carbon only has 4 valence electrons, where sulfur has 6. So if you work out the structure of the carbon dioxide for both carbon and oxygen to follow the octet rule with 16 electrons, valence electrons, there is a double bond between both the carbons, both carbon and oxygens, both the oxygens and carbons. So this molecule has only 2 things around the carbon, the 2 oxygens with their bonding electrons. So this molecule is a linear molecule. And although the bond is a polar covalent bond, the molecule is not a dipole.
There's too many electrons.
Yeah, you're right. Sorry. Let me take them away. Let me take them away. You are right. There we go. Take 2 away. Thank you. Now here you have a non-polar molecule. What must I hold on to?
No, it's fine. You answered.
I wish I could speak like you, bro. That guy's accent is so cool.
So this molecule is non-polar. What will the intermolecular force be between carbon dioxide molecules?
It would be dispersion forces.
Oh, come on.
London forces.
Give me what I want. London forces.
I don't think that bicycle
It's just easier to remember.
Which molecule will have which substance will have the higher boiling point?
It will be.
They're both gases at room temperature. Which one will turn into a gas first?
No, sulfur dioxide. No. It's carbon dioxide. Because
Carbon dioxide will have the lower boiling point. You got it?
Because London forces are weak.
It's not a dipole. The oxygen is negative and the oxygen is negative. That's all that's sticking out. The carbon isn't sticking out. So the carbon would have been positive. It's not a dipole, even though you have a polar covalent bond. So if I compare carbon dioxide to sulfur dioxide, carbon dioxide has London forces, which are weaker than dipole-dipole forces. And sulfur dioxide's got dipole-dipole forces. Okay. Can I go to the next slide so that I can write this down? Pardon?
On the carbon
It's fine.
dioxide.
Pardon?
I only see the double bonds. Where's the rest?
There are the double bonds.
Yeah, where's the side ones? Why didn't you put the side ones?
Sorry, what are you talking about?
These X's, man, why didn't you put them on that structure?
Because the Cooper structure you don't have to show.
Oh, okay. We've been doing it for a while.
Sometimes do.
London forces are weaker than type forces.
If you compare molecules that are similar, you can say London forces are weaker than dipole-dipole forces. But you do get London forces that are much stronger than dipole-dipole forces.
Like?
I'll explain to you just now, okay? Just give me a moment.
Carry on.
Can I carry on?
Yes, ma'am.
So, I'll just
Wow.
London forces